The reversal law for inverses. Welcome, everyone. Today, we are going to explore a very important property in matrix algebra known as the reversal law for inverses. Now, when we are working with matrices, we often encounter situations where we have to deal with the product of two or more invertible matrices. You might be wondering if finding the inverse of such a product is as simple as finding the inverse of each matrix individually. Well, it actually follows a very specific and crucial rule. This law states that the inverse of a product of two non-singular matrices is equal to the product of their inverses. But, and this is the key part, they must be taken in reverse order. As we move through the next few slides, we will look at the formal definition, prove why this happens, and I'll even share a simple real-world analogy to help you remember why that reversal is so important. Theoretical definition. Now that we have introduced the concept of the reversal law, let's look at the formal theoretical definition. Suppose we have two matrices, A and B. For this law to work, we need to satisfy a few conditions. First, both A and B must be non-singular square matrices of the same order, and the product ob must exist. If these conditions are met, then the inverse of the product ob is equal to the inverse of B multiplied by the inverse of A. Notice how the order has swapped. Now, this is a very important point to remember, and it's where many students trip up. The inverse of ob is not equal to the inverse of A multiplied by the inverse of B. Why is that? It is because, in the world of matrices, multiplication is not commutative. In simpler terms, unlike regular numbers where 2 times 3 is the same as 3 times 2, in matrix algebra, A times B is generally not the same as B times A because the order of the original multiplication matters. The order of the inverse must be reversed. We will see a formal proof of why this must be the case in the next slide. Verification of the law, the proof. Before we dive into the algebra, we need to remember the fundamental rule for verifying an inverse. To prove that a matrix X is indeed the inverse of a matrix Y, you must demonstrate two things. First, that Y multiplied by X results in the identity matrix, and second, that X multiplied by Y also results in the identity matrix. In our case, we want to verify if the expression B inverse times A inverse is truly the inverse of the product A times B. Let's walk through the proof step by step. In step 1, we will begin by multiplying the original product, A times B, by our proposed inverse, B inverse times A inverse, from the right side. So we write out A times B, all enclosed in parentheses, multiplied by B inverse times A inverse, also in parentheses. Now, using the associative property of matrix multiplication, which allows us to regroup terms, we can shift our focus to the middle. This gives us A, multiplied by the quantity B times B inverse, all multiplied by A inverse. Moving to step 2, we simplify this using the fundamental property of inverses. We know that any matrix multiplied by its inverse results in the identity matrix. Therefore, B times B inverse simplifies to I, the identity matrix. This leaves us with A, multiplied by the identity matrix, multiplied by A inverse. Since multiplying any matrix by the identity matrix doesn't change it, this further simplifies down to just A times A inverse. Finally, in step 3, we reach our final simplification. Applying that same property of inverses once more, we know that A times A inverse equals the identity matrix, or simply, I. By showing that this multiplication results in the identity matrix, we have successfully completed the first half of our verification. In the next slide, we will perform the same process from the left side to complete the proof. Now that we have established the theoretical definition of the reversal law, let's move on to slide 3, where we will actually prove why this law works. Verification of the law continued. Now, up until this point, we have successfully shown that, when we multiply the product ob by our proposed inverse from the right, we arrive at the identity matrix. But to be mathematically rigorous and truly prove that B inverse A inverse is the inverse of ob, we must also complete the check from the other direction. In step 4, we are going to multiply the product ob by B inverse A inverse from the left. So we start with the expression, B inverse A inverse, all multiplied by a B. To simplify this, we can use the associative property, which allows us to regroup the matrices without changing the result. Notice how I've moved the parentheses to group A inverse and A together. This gives us B inverse, multiplied by the quantity A inverse times A, all multiplied by B. Now, we apply the fundamental property of inverses that we discussed earlier. Any matrix multiplied by its inverse results in the identity matrix. So, A inverse times A becomes the identity matrix, represented by the letter I. This leaves us with B inverse, multiplied by the identity matrix, multiplied by B. Since multiplying any matrix by the identity matrix doesn't change it, we can simplify this further to just B inverse times B. And once again, applying that same property of inverses, B inverse times B simplifies down to the identity matrix, or simply I. So, looking at what we have achieved, we have shown that multiplying from the right results in the identity, and multiplying from the left also results in the identity. Because both directions yield the identity matrix, we can officially conclude and state the reversal law. The inverse of A times B is equal to B inverse times A inverse. This mathematical proof sets the stage for the next slide, where I'll share a very simple real-world analogy to help you intuitively remember why this reversal is so important. Real-world analogy, the shoe sock principle. Now I know that the mathematical proof we just walked through in the previous slides might seem a bit abstract. To make this concept more intuitive, let's step away from the algebra for a moment and look at a real-world analogy, often called the shoe sock principle. Think about your morning routine when you're getting ready to leave the house. We have two distinct actions here. First, there is action A, which is putting on your socks. Second, there is action B, which is putting on your shoes. When we perform these actions one after the other, we can represent this combined operation as A times B in this sequence. You perform action A first, followed by action B. Now, here is the crucial part. Suppose you want to reverse this entire process to return to your original state. Essentially, you want to find the inverse of what you just did. If you try to undo the operations in the same order, you'll run into a problem. You cannot take off your socks first while your shoes are still on. To successfully reverse the process, you must undo the operations in the exact opposite order. You must first perform the inverse of action B, which is taking off your shoes. Only after the shoes are off can you perform the inverse of action A, which is taking off your socks. So, just as you must take off your shoes before your socks, in matrix algebra, the inverse of the combined process A times B is equal to B inverse times A inverse. This perfectly illustrates why the order must be reversed in the reversal law. Now, let's see how this principle holds up when we apply it to actual numbers in our next slide. Numerical example. Now that we have understood the theory and the logic behind the reversal law, let's put it into practice with a concrete numerical example. On this slide, we are going to verify the law using two 2x2 matrices. First, let's look at our given matrices. We have matrix A, which is 1, 2, 0, 1, and matrix B, which is 1, 0, 3, 1. Our first goal is to find the product of these two matrices, which we call A times B. To do this, we multiply the rows of the first matrix by the columns of the second. For the top left element, we multiply 1 by 1 and add 2 times 3, which gives us 7. For the top right, we multiply 1 by 0 and add 2 times 1, resulting in 2. Moving to the bottom row, 1 times 1 plus 3 times 1 gives us 3, and finally, 0 times 0 plus 1 times 1 gives us 1. So, our resulting product matrix, OB, is 7, 2, 3, 1. Next, we need to find the inverse of this new product matrix, which we denote as OB inverse. To find the inverse of a 2x2 matrix, we first need to calculate its determinant. For our matrix OB, the determinant is 7 times 1 minus 2 times 3, which simplifies to 7 minus 6, leaving us with a determinant of 1. After finding the determinant, we find the adjugate of the matrix. To get the adjugate, we swap the elements on the main diagonal and change the signs of the other two elements. This gives us a matrix with 1, -2, -3, and 7. Finally, to get the inverse, we multiply the reciprocal of the determinant by this adjugate matrix. Since our determinant is just 1, the inverse remains the same. So, the inverse of ob is 1, -2, -3, and 7. Keep this result in mind, because in the next slide, we are going to find the individual inverses of A and B to see if multiplying them in reverse order gives us this exact same result. Numerical example continued. Now that we have found the inverse of the product, which we calculated in the previous slide, we need to find the individual inverses of matrices A and B to see if they follow the reversal law. Let's move on to step 3, where we find A inverse and B inverse individually. First, looking at matrix A, the determinant of A is 1, and the adjoint of A is the matrix with 1, -2, 0, and 1 in the respective positions. Since the determinant is 1, the inverse of A is simply that same adjoint matrix, 1, -2, 0, and 1. Next, let's look at matrix B. Similarly, the determinant of B is 1, and the adjoint of B is 1, 0, -3, and 1. Therefore, the inverse of B is also equal to its adjoint, 1, 0, -3, and 1. Now, for step 4, we perform the most crucial part of this verification. We calculate the product of these two inverses, and remember our reversal law, we must multiply them in the reverse order, which is B inverse times A inverse. We take the matrix B inverse, which is 1, 0, -3, and 1, and multiply it by matrix A inverse, which is 1, -2, 0, and 1. When we perform the matrix multiplication, we multiply the rows by the columns. For the top left element, 1 times 1 plus 0 times 0 gives us 1. For the top right, 1 times -2 plus 0 times 1 gives us -2. Moving to the bottom row, -3 times 1 plus 1 times 0 gives us -3, and finally, -3 times -2 plus 1 times 1 gives us 7. This results in a final matrix of 1, -2, -3, and 7. To reach our conclusion, notice that the result we just calculated for B inverse times A inverse is exactly the same as the inverse of the product ob that we found back in the previous slide. Since both sides equal the matrix 1, -2, -3, and 7, we have successfully verified the reversal law. Common mistakes. First, the most frequent error I see is ignoring the order. Many students instinctively write that the inverse of A times B is equal to the inverse of A times the inverse of B. Please, do not do this. As we saw in our proof and our numerical example, you must always remember that the order of the matrices must be swapped. You are reversing the sequence. Second, be careful not to assume commutativity. In basic algebra with numbers, the order of multiplication doesn't matter, but in matrix algebra, it does. You cannot assume that because A and B are invertible, you can multiply them in any order you like. Always keep in mind that the inverse of B times the inverse of A is generally not the same as the inverse of A times the inverse of B. Finally, a very important technical point. Do not try to apply this law to singular matrices. The reversal law only works if both A and B are non-singular, meaning they must be invertible. If the determinant of A equals 0 or the determinant of B equals 0, then the inverse simply does not exist, and the law cannot be applied. Now, before we wrap up today's lesson, I want to pause and highlight some common pitfalls. Even if you understand the theory, it is very easy to make a mistake during an exam if you aren't careful. In our final slide, we will summarize the key takeaways to ensure you have a solid grasp of this concept. Key takeaways. First, let's restate the core formula. Always remember that the inverse of the product of two matrices, A and B, is equal to the inverse of B multiplied by the inverse of A in mathematical terms. We say, the quantity A times B, all raised to the power of -1, equals B inverse times A inverse. Now, if you ever find yourself doubting whether to swap the order, just think back to the shoe sock analogy we discussed earlier. The logic is simple. To undo a sequence of operations, you must undo the very last operation you performed first. You can't take off your socks until you've taken off your shoes. However, there is a crucial requirement to keep in mind. This law only works if both matrices are square and non-singular. As we saw in our numerical examples, if the determinant of either matrix is 0, the inverse simply doesn't exist, and the law cannot be applied. Finally, it is worth noting that this principle isn't limited to just two matrices. It extends beautifully to any number of matrices. For instance, if you have a product of three matrices, A, B, and C, the inverse of that entire product would be the inverse of C times the inverse of B times the inverse of A. The pattern remains the same. Just reverse the order and apply the inverse to each. All right, we have reached the end of our lesson. Let's wrap everything up by reviewing the key takeaways from today's session on the reversal law. That concludes our lesson. Make sure to practice those matrix multiplications to ensure you're comfortable with the reversal process. Great job today!